Okay, we'll start this lecture on Chapter 3. This chapter is about ionic bonds and ionic compounds. First, to start, one of the main things to be able to do whenever you're looking at either a formula or given a name for a compound is to be able to identify whether it's ionic or covalent. This is a very important thing to be able to do in order to write proper names and write proper formulas. So one of the main distinctions between them are that ionic compounds, generally that are formed from ionic bonds, form between a metal and a nonmetal. And we talked last time about where you can find those on the periodic table. And covalent bonds and then covalent compounds will form between two nonmetals. So when you're looking at a formula or a name, you need to identify, and we'll be dealing with binary compounds and those with polyatomic ions predominantly. So you need to identify whether you're looking at two metals, well, not two metals, whether you're looking at two nonmetals or a metal and a nonmetal. If you're looking at two nonmetals, then that's a covalent compound or a molecule. If you're looking at a metal and a nonmetal, then that's an ionic compound. So moving on from there, ionic compounds are joined by ionic bonds. Ionic bonds are those where electrons are transferred from one of the atoms to another, resulting in ions. A covalent bond, leading to covalent compounds, is a bond where the atoms will share those electrons between them. And the common analogy here is to think of a covalent bond like a tug of war, where one atom is pulling on the electrons in that bond and the other atom is also pulling, and we'll talk a little bit later about when there's sort of unequal pulling, what we call that. But for now, that bond is one where the electrons are shared between them. You will see use of what are called ball and stick models and space filling models. I think you'll actually work with the ball and stick models in the lab when you start talking about molecular shape. And these just help to visualize the compounds. You can see here some simple compounds and the atoms and how they are joined together. This I've mentioned a bit already. So ionic bonds, these are ones where there's a transfer of one or more electrons from one atom to another. It is a metal bonded to a nonmetal. The ion that results is that charged particle, either positively or negatively charged. And then to denote the two, a cation is an ion that's positively charged, and an anion is one that's negatively charged. Some important points here. Metals tend to lose electrons and form cations. So the metals, specifically, we'll look at those in groups 1A and 2A quite a bit. And anions are usually formed from nonmetals. And these are ones that will gain electrons to form anions. So because electrons are negatively charged, if you're adding more electrons than they would normally have, then they'll end up negatively charged. Likewise, if you're removing electrons, you're removing a negative charge, so it leaves a positive charge result. Here's showing one of those types of reactions, so how sodium chloride forms. It is an ionic compound, and in that sense, one electron is transferred from the sodium atom to the chlorine atom, and you'll see that the sodium has lost an electron. It's represented there with the sodium being the cation with a +1 charge, chlorine with a -1 charge. It's worth noting that oftentimes we don't write the ones in the charges. We write other numbers, 2s, 3s, etc. But if you just see a plus or a minus, that's indicating +1 or -1. One other thing to note when you're looking at different types of molecules and trying to write formulas, this doesn't really fit anywhere in particular, but it's worth mentioning, is that there are elements that exist as diatomic molecules when they are existing as themselves. So for example, when hydrogen is in the air, it always exists as H2, as two hydrogen atoms bonded together. These are referred to as diatomic molecules. Two atoms joined together is the diatomic part of that. And you should either memorize or write down on your exam sheet those elements that form diatomic molecules when they are in their elemental form. Those would be hydrogen, nitrogen, oxygen, fluorine, chlorine, bromine, and iodine. They're listed on the bottom of page 99 if you didn't get any of those listed. Those, again, all will exist in, and they're also shown in a figure on page 100. They'll all exist in that diatomic form when on their own. So when, for example, if you're writing a chemical reaction and it says hydrogen gas, you would know to write H2. Or if it said oxygen gas, you would write O2. Or nitrogen gas, N2. As opposed to a reaction saying helium gas, and that would just be He. It does not exist naturally as a diatomic molecule, exists just as a single He molecule. And that goes to the case for the rest of the elements on the periodic table, with the exception of those we just listed that exist as diatomic molecules. Okay, so again, just keep that in mind, and it doesn't fit exactly in here with the ionic bonds, but it is important. Next, a little bit about some charges. So one of the things to be able to do here is to predict a charge on an ion, and there's a fairly simple way to do that. I've mentioned by now that the group numbers in the periodic table are important. Here's another reason that they give us information. So group 1A and 2A elements, these are metals on the far left of the periodic table, with the exception of hydrogen, are going to form, they're going to lose an electron and form cations. And so the group 1A elements have one valence electron, that we talked about last time. So they would like to lose that one valence electron, and as such they form ions with a +1 charge. So you'll see here lithium with a +1, sodium with a +1, potassium with a +1. Likewise for group 2A, they have two valence electrons, and so they will tend to lose those two valence electrons when forming compounds and form the ions that you see there. So beryllium +2, magnesium +2. There's really no difference as to whether you put 2+ after the magnesium or +2. You'll see it written both ways, so just know that there's no difference there. Some texts write the plus first and some write the number first. If we look at some of the other main group ions, you can see those in group 7A. They have 7 valence electrons. They will tend to gain an electron and thus form ions with a -1 charge, since they've gained that negatively charged electron. So fluorine -1, chlorine -1, bromine -1. Likewise with 6A, they have 6 valence electrons. They would like to gain 2 electrons, and so they typically will take on charges of -2. Nitrogen typically take a charge of -3. You can see some others there in group 3 and group 4. Aluminum is typically +3, gallium +3. Lead, you can see some can be either +2 or +4. What I will ask is that you are able to predict charges for ions given group numbers. You'll see in a little bit more information about how to do that, but for now, you're looking to either gain or lose electrons such that you have a filled octet or a filled shell. And what that means at the moment is that group 1A would lose 1 electron, 2A would lose 2 electrons, group 5A would gain 3, 6A would gain 2, and 7A would gain 1. And we'll talk a little bit more about that when I talk about the octet rule. But you should be able to predict the ions that you see here and their respective charges from their positions in the periodic table. Otherwise known as their group numbers. Now some transition metals, and we've seen this already, that a lot of the higher atomic number elements can do some different things. Here's another example. Some transition metals will form more than one cation. You would need to be given information about the charges on these. I will not ask that you can predict what the charges of these will be. One of the ways that you will be able to know what the charge is from the name, which we'll get to next. So again, an ionic compound, this is where you're forming a compound with a cation and anion. Another really important piece here is that the compound itself always ends up as a neutral compound. That means that the charges on the ions must cancel each other out in order to leave a net charge of 0. So I'll explain a little bit about how that works here. So you can see 3 examples there under binary ionic compounds. I'll come back to the names in a little bit, but first, just in terms of forming or writing a formula. If you're given sodium chloride and you know you have sodium ions and chlorine ions, you look at the periodic table, figure out what groups they're in. You find that sodium will be sodium with a +1 and chlorine will be chlorine with a -1. You're going to combine those ions together in small whole number ratios such that the charges balance each other out and equal 0. You can see in this case it's just a 1-to-1 ratio, right? +1 - 1 equals 0. So you'll see the formula is written NaCl because the Na with the plus charge and the Cl with the minus charge cancel each other out, leaving a net charge of 0. If you look at the next compound, magnesium oxide, magnesium has a +2 charge, oxygen has a -2 charge. You can see here that a 1-to-1 ratio between magnesium and oxygen ion, oxide, would balance each other out and give you a net charge of 0, +2 and -2. So the formula is written MgO, 1 magnesium to 1 oxygen. A note here, sometimes students will put Mg2O2, and so what I'll say is that as you're writing formulas, you always want to look to see if you can reduce all of your numbers, so divide through all of your numbers by the same number. So in the case of Mg2O2, you could divide both of those by 2 and get 1, and that would be the proper way to write that formula. Again, you're balancing out those charges in the simplest, smallest whole number ratio to write those formulas. Let's look at the last example. So aluminum sulfide, aluminum has a +3 charge, sulfur has a -2 charge. So here becomes a little bit more complicated, but not impossible. +3 and -2 do not net 0. You need to find a way to combine the aluminum ions with a +3 charge and the sulfur ions with a -2 charge to give you small number or small whole number ratios that cancel each other out. Here's a trick for this. If you take the charge on the anion and put it as the subscript for the cation, so take the 2 from the sulfur and put it as the subscript for aluminum, and then take the charge on your cation, aluminum, and put it as the subscript for your anion, sulfur, you'll see the 3 there. Essentially what you're doing here is you're accounting for those charges and you're multiplying each of them respectively so that you end up with a net charge of 0. You might want to write this one down while I'm talking through it just to prove it to yourself. So if we have 2 aluminum ions, as is written in the formula, Al2S3, that means 2 aluminum ions. Each of them have a +3 charge. So the total charge on aluminum is +6. The sulfur, on the other hand, in the formula, we have 3 sulfur ions. Each sulfur ion has a charge of -2. So the total charge on sulfur is -6. So we have +6 for the total charge on aluminum and -6 for the total charge on sulfur. And so the net charge is 0. So the formula is correctly written. Again, the way to go about this, sort of the trick there, is to use the charges and essentially swap them and place those as subscripts. The caveat here is you need to make sure that you can't divide through by the same number and get smaller numbers. So again, if you look at magnesium oxide, if I use that same skill, I would end up with Mg2O2. But I can divide all the way through and end up with MgO, which you should always do. Let me say it differently. Mg2O2 would be incorrect on an exam. So always make sure that you go back and go and divide through by any number that you can to make those the smallest ratios. And then go back and make sure that those charges do in fact cancel each other out. I guess I should have mentioned that those subscripts that you see there are indicating how many of each of those things you have. And ones are not written. So NaCl means 1 Na and 1 Cl. MgO means 1 Mg, 1 O. Al2S3 means 2 aluminum and 3 sulfur together in that compound. Now the way that we name these is by taking, well, first notice that the way we wrote the formula is we put the cation and then the anion. That is always the case. So when you are writing formulas for ionic compounds, you want to make sure that the cation goes first and the anion goes second. Once you've done that, then in terms of naming them, the cation is named by just its name from the periodic table. So Na is sodium, Mg is magnesium, Al is aluminum. The anion part of the name, you take the name from the periodic table and essentially chop off its ending and add IDE. So chlorine becomes chloride, oxygen becomes oxide, sulfur becomes sulfide. So when naming binary ionic compounds, first the formula is always written cation then anion. The cation is just the name as written on the periodic table, and the anion gets that IDE ending. Essentially you drop part of the ending off the element's name and add IDE. This takes a little practice, but I think you'll get the hang of it. So that's the simplest way to name ionic compounds. These are all ones where you would be able to predict their charges. So these are based on where they are in the periodic table. It's sometimes not apparent, some of the ones that I showed you back here, where some of these metals form different, more than one cation, and I said that you wouldn't be able to predict that necessarily from the group numbers. So in those cases, when naming them, we include the charge on the cation in the name. So if you look at the first one, you'll see that that's iron with a +3 charge and oxygen with a -2 charge. You'll see the formula Fe2O3. First, the formula, again, swap the charges. So the -2 on oxygen, the +3 on iron get swapped and give us Fe2O3. Let's check that against the charges. So I've got 2 iron ions. Each have a +3 charge. So the total charge on iron is +6. I have 3 oxygen ions. Each oxygen ion has a charge of -2. So the total charge on oxygen in that compound is -6. +6 and -6 give us 0. So we're okay there. Now in terms of naming this, that iron is one of those that you wouldn't be able to predict based on its group location. And this just is, generally speaking, the transition metals fall in this category. So in order to name it, we're going to actually include the charge on the iron in the name. So you'll notice there it says iron, and then in parentheses, Roman numeral 3. That Roman numeral 3 tells you that it's iron with a +3 charge. And we're only going to be dealing with these for cations. So you'll see them all written for cations this way. So iron 3 oxide. The ending oxide is the same as what we did before. Look at the other two names. So tin 2 chloride. Again, the 2 in parentheses tells you the +2 charge on tin in that compound. The third one, lead 2 fluoride. Again, lead tells you that +2, that it has a +2 charge in that compound. If we go and look at the formulas written here, so tin 2 chloride, so we've got tin with a +2 charge. Chlorine, we look at its group number, it's in group 7, so it has a -1 charge. We swap the charges there, we get SnCl2. Recall that the ones aren't written. So we go back and check those. We have 1 tin with a +2 charge, so total charge on tin is +2. We have 2 chlorine ions, each have a charge of -1. So total charge on chlorine is -2. +2 and -2 give us 0. The last one, lead 2 fluoride. Again, swapping those charges, you end up with lead PbF2, so 1 lead and 2 fluorine ions in that compound. Check the charges. We have 1 lead with a +2 charge, so the total charge on lead in that compound is +2. We have 2 fluorine ions. Each of them have a -1 charge. Total charge on fluorine there is -2. So +2 and -2 give us a net 0 charge. As I'm talking through these, if you want to replay this and do it again, I'd suggest you write these down and sort of walk through the steps here of the charges as I'm talking through them. This is a very important concept to have that will allow you to write the formulas correctly, understand the charges, and how those relate to writing these formulas. So definitely something to practice. Another thing that comes into play with naming ionic compounds is the use of polyatomic ions. So we often see compounds that have polyatomic ions in them. A few notes on this. I would either, you can photocopy this table if you want and put it on your exam sheet, or you can handwrite it. It's entirely up to you. It doesn't matter to me which you do, but you'll want to make sure that you have this on your exam sheet, unless you want to memorize all of them. So you need to know both the formula and the name in order to write names and then write formulas from names. So you'll see that each of these particular polyatomic ions has a specific name associated with it. When you're naming compounds that have polyatomic ions in them, you use just the name that's given here for that polyatomic ion. So I'll show you a couple of examples here. Notice that there are a lot that just have a minus charge. That is a -1. We'll call that ones aren't written. And the polyatomic ion you need to think of as an entire unit, an intact unit. So in other words, acetate is always CH3CO2 with a -1 charge. And that -1 charge is over that whole polyatomic ion. It's not just for that oxygen. It's over the whole thing. Cyanide is CN with a -1 charge. So the -1 is over that whole polyatomic ion. And when you see them written in formulas, you'll see parentheses actually written around them to denote that they are together as a unit. So let's take a look at how we name with these polyatomic ions. So first I'll start with a name to formula. So you're given a name, sodium hydroxide. Sodium you're familiar with, you know that that's a cation. You look and see it's on group 1, so that's Na plus, or +1 charge. Hydroxide, you don't remember that being on the periodic table, so you automatically look at your polyatomic ions chart. And yes, that's what I would suggest you do. Notice from that chart that there's only one ion that's positively charged, and that's ammonium. The rest are negatively charged. So if you're looking at a name and you're looking at the second part of the name, always make sure that that is not a polyatomic ion before you proceed further. So check the polyatomic ion chart first, then solve after. So if you don't have a polyatomic ion, then go back to the rest of the rules that you have. But always check that polyatomic ion first. So you look your polyatomic ion chart and you see hydroxide is listed there, and it's listed as OH-. So that means OH with a -1 charge. You do the same thing here in writing formulas as you did before. Swap the charges. So the -1 on OH becomes that 1 on Na that you don't see because ones aren't written. And the +1 on Na becomes a 1 outside of the OH. Again, it's a 1, so you don't see it written. So the formula here, NaOH. Now specifically, this is sodium with a +1 charge and hydroxide with a -1 charge. And those cancel each other out and leave you 0. The same rules apply here. You must make sure that your charges cancel each other out and leave you a 0 net charge. So let's take the next one, magnesium carbonate. So magnesium, you look up, it's in group 2. You know that means it's magnesium with a +2 charge. You look at your polyatomic ion chart and you find carbonate is CO3 with a -2 charge. You take that -2, I'm sorry, excuse me. if you look here, you've got magnesium with a +2 and carbonate with a -2. You could swap the charges, in which case you'd end up with Mg2 and then CO3 in parentheses with a 2 outside of that. Then you would realize you could reduce by dividing by 2 and end up with what you see there, MgCO3. That's the simplest ratio between those two ions. So that is the correct formula as written. The +2 charge on magnesium cancels out the -2 charge on the carbonate, leaves you with a 0 net charge. Okay, the next one, sodium carbonate. So we look up sodium, it's in group 1, so it has a +1 charge. Carbonate's on my periodic table, it's CO3 with a -2 charge. I swap those charges and I end up with a formula Na2CO3. So let's check that. I have 2 sodium ions, each with a +1 charge. So total charge on sodium is +2. I have a single carbonate polyatomic ion that has a charge of -2. So the -2 and the +2 cancel each other out. The last one, iron 2 hydroxide. So I remember that when I see those parentheses with the Roman numerals, that tells me the charge. So that tells me it's iron with a +2 charge. Hydroxide off my periodic table is OH with a -1 charge. I swap those charges. Here's an example of what I was saying before about using parentheses around polyatomic ions. So I need 2 hydroxide ions here to balance out the +2 charge on iron. So I put parentheses around the whole thing, the whole polyatomic ion, OH, and a 2 outside. So that means 2 hydroxide ions. So let's check. I've got 1 iron ion with a +2 charge and 2 hydroxide ions, each with a -1 charge. So total charge there is -2. +2 and -2 cancel each other out. Okay, hopefully this has given you enough examples of writing the formulas and where the names are coming from. There's more practice in your pre-class assignment as well as your homework, and certainly there are more examples in your text as well. These are really some key skills to know, so naming compounds, writing formulas, you're going to need to be able to do throughout the semester, so please make sure that you get the practice that you need to be proficient at this. Okay, we talked a little bit about knowing those charges. This gives a little bit more information as to why that's the case. So if we look at electron configurations of ions, so here, for example, sodium and chlorine, and we said sodium would want to lose an electron and form sodium with a +1 charge, and chlorine would want to gain an electron to form chlorine with a -1 charge. And here you can see what's happening in terms of their electron configuration. So when sodium loses an electron, it loses it from its outermost shell, which is that 3s. And you can see that Na+1 has 1s2, 2s2, 2p6 configuration. If you look next at chlorine, you'll see when it gains an electron, it fills that 3p6 orbital. And these are key points. So atoms want to gain or lose electrons to end up with full shells. So for sodium, that means losing that electron so that it has a full shell underneath. And for chlorine, it means gaining an electron so it now has that full p subshell and full orbitals. Again, this is just some of those main group ions, and what is referred to here is their noble gas configurations. This is another way of saying, I mentioned before about this octet rule, so atoms want to get to 8. They either want to lose or gain electrons to have 8 electrons in their outermost shell. And I'll show you some more examples of that in a bit. But here's how that plays out. Again, the group numbers tell you how many electrons they want to gain or lose to get to that magic 8. So group 6A want to gain 2 electrons. Group 7A want to gain 1. Group 1A and 2A want to lose 1 electron and 2 electrons respectively. Group 3A want to lose 3 electrons. So the reason that we see the charges that we do on ions is because of this chemistry that they have. Here's an example of iron either losing 2 electrons or losing 3 electrons, and those transition metals, when we start getting into the d orbitals and then f orbitals further up, there are different configurations that make atoms more stable. So that's where you're going to see some of the some of the fluctuations and alternatives here, not just sort of one charge, but multiple. Okay. A little bit here about ionic radii. We talked about atomic radius in the previous chapter. Recall that we talked about the trend for atomic radius increasing down a group in the periodic table, and that was because we were adding electrons to their, adding whole shells of electrons. And we also talked about how atomic radii decreased from left to right, and that was because that effective nuclear charge increased as we went across a row. So here we're talking about ionic radii and sort of comparing the two. So what you see in this table are two series. So lithium, sodium, potassium, rubidium, and cesium in what's denoted A, and beryllium, magnesium, calcium, strontium, and barium in B. And the blue is showing you the atomic radii, and then the purple are showing you the ionic radii for each of those. So a few things to note. One is that we see the same general trend of increasing down a column. So when we look lithium through cesium, so that's group 1, as we go down that column, we see both the atomic radii increase as well as the ionic radii. And you can see the same thing for group 2. So as we go down group 2, that's starting at beryllium, we see the atomic radii increase. We also see the ionic radii increase. So that trend is generally the same for both ionic radii and what was I saying? And atomic radii. Now, also what you're looking at here are cations. Okay, so the group 1A and 2A forming cations. And if you look, you can see another trend here in terms of the comparison between their neutral atom and their cation. So, and that's sort of stated here at the bottom, that the cations are smaller than their corresponding neutral atoms. So Li plus 1 is smaller than a lithium atom. And if you think about that, the Li plus 1 has lost an electron. That means that it's lost an electron from that outermost valence shell. So it's, as it says here, their principal quantum number is smaller, again, because it's lost that electron. And their effective nuclear charge is larger because you're essentially just dropping down to that next shell. And that's the case, again, for the series in beryllium as well. You can see the comparison of any of the cations are smaller than their corresponding neutral atom. If we look at anions, on the other hand, so anions, again, would be ones that are gaining electrons. And as you might expect, so they're gaining electrons, they're going to be larger, their radii are going to be larger than their corresponding neutral atom. And again, they have an extra electron, so there's more electron-electron repulsions, and they have a decrease in their effective nuclear charge too. Okay. There are two sort of concepts here. Actually, I should have said before, a couple of sections I'm not going to cover are starting at 3.12 through the end of the chapter. It gives you some general chemistry of several of the groups. We'll actually cover that when we look at reactions themselves, so I'm not going to specifically go through those or ask you to know those from this chapter. Anyway, back to this. So ionization energy and electron affinity, these are two concepts from this chapter that you should know and be able to work with and make predictions from. So here's the first. Ionization energy, it's abbreviated a capital E with a subscript I. This is the amount of energy that's needed to remove the highest energy electron from a neutral atom in its gaseous state. So shown here at the bottom is what's the amount of energy that would be needed to remove an electron from an atom of hydrogen. And you can see that energy is 13, fairly large, 1,312 kilojoules per mole. So it's represented by, again, removing that highest energy electron. Obviously, hydrogen only has one, probably not the best example, but we're looking at those valence electrons. So those electrons in the outermost shells of atoms of higher atomic numbers. So we do see some general trends here for ionization energy in terms of the periodic table. Typically, the ionization energy will increase as you go across a period and generally decrease as you go down a group. That's not really shown clearly here, but that is the general trend. A few other things to note here, and this just points to the specific chemistry of these atoms, is that you have maximum values of ionization energies for the noble gas elements in any particular period as you're going across. And again, that's because we're talking about removing an electron, and those noble gases do not want to lose electrons. They also don't want to gain electrons. They're essentially in a perfect state, if you will, and have just as many electrons as they want and don't want any more. So they will have high ionization energies because, again, we're talking about the energy that's needed to remove an electron, and they don't want to lose electrons. So the energy required to remove those electrons is really high for them. If you're talking about, on the other end, if you're talking about atoms in, say, group 1, they would like to lose that electron. So they're going to have relatively low ionization energies, as is reflected on the chart that you see here. So it corresponds to what we know about that magic 8 octet rule and whether atoms will want to gain or lose electrons. We do see some slight, I don't know, it's not really anomalies, but it's just irregular from the pattern, a trend that we saw. And that's for the 2A elements have slightly larger ionization energies than you might expect. But if you consider that they have a filled 2s orbital, that electron, removing that electron from the 2s orbital is slightly unfavored. So you're going to see their energies be a little bit higher than you might predict. And oxygen has lower because it's the first electrons removed from a filled orbital. Okay, we can also talk about second and third ionization energies. So these would be removing the second highest energy level electron, then the third highest energy level electron. I am not going to go through those for the context of this course, but know that we do know those ionization energies. We have predicted them, and generally speaking, if you look here, so if you look down any of these columns, you'll notice that as we remove the second and then the third and then the fourth electrons, those amounts of energies increase fairly dramatically. So typically the lowest amount of energy is to remove the first electron. If we're talking about removing second and third, then it takes more and more energy to do that. Okay, the other concept here is electron affinity. This is essentially the reverse. I like to think of this, or call this electron love. And so this is the energy change that occurs when an electron is added to an atom. So in ionization energy, recall we were looking at what's the energy that's needed to remove an electron from an atom. Here we're talking about the energy change that occurs when an electron is added to an atom. So if, for example, an atom really wanted another electron, it would have a high electron affinity. So if you think of affinity as like for or attractiveness for, so the higher that is reflecting the fact that it really would like to get another electron. So if you look at the ones that are highest here, fluorine, chlorine, bromine, iodine, and you look at where those are in group 7. They would really like to gain that other electron to have that octet. So they have relatively high electron affinity values, because again, that reflects the energy change that would occur when they added an electron to themselves. So, and if you look on sort of the opposite side, if we look at group 2A elements and group 8A elements, the noble gases and alkaline earths, they would rather not gain any electrons. You'll see that they are low on that scale. In terms of the negative value that you see here, this is just showing you that that's the amount of energy that's released when an electron adds to an atom. So the more negative the number, the higher the electron affinity. I know this is sort of counterintuitive, but when we talk about fluorine at, what is that, minus 300 and say 25, that's the amount of energy. So 325 kilojoules per mole, that's the amount of energy that will be released when fluorine gained that electron. Okay, so it has a very high electron affinity. So the more negative the electron affinity, the higher the electron affinity is. So again, fluorine, chlorine, bromine, these have all high electron affinities. Group 2A and group 8A elements, they have very low electron affinities. And in fact, we don't even measure electron affinity in a positive direction because it can't be measured. They essentially don't want to add electrons, so it's not a measurable quantity. So you'll just see them written on the 0 mark. Okay, I've mentioned this by now, and hopefully this is making some sense. So for the most part, the main group elements, and that's what we will focus on in this course. We will not focus on chemistry of transition metals much. So the main group elements, the lanthanide and actinide series, main group elements tend to undergo reactions that leave them with 8 outer shell electrons, whether that means losing so that the shell underneath has 8, or gaining so that the current shell builds up to 8. So group 6A and 7A want to gain electrons to build up to 8. Group 1A, 2A, and 3A want to lose electrons to drop down to their full shell underneath. They all want to get to this noble gas configuration. That's another way that it's stated. Again, noble gases have full shells. They have octets. So that's where the naming comes from here. And again, they will react to be able to do this. So metals, again, those are groups 1 and 2, so they tend to have low ionization energies and low electron affinities. They want to lose 1 or more electrons. Nonmetals tend to have high ionization energies and high electron affinities. They tend to gain 1 or more electrons. So if you think about that, high ionization energy means that's the energy needed to pull off an electron. They don't want to do that, so that's why they would have a high ionization energy. High electron affinity would mean they have an affinity for gaining electrons, which they do. So notice that the trend here, the two concepts, go together. So nonmetals have high ionization energies because that's the amount of energy to pull off an electron. They also have high electron affinities because they love the electrons they have, and they would like more. Okay, kind of shifting gears here a little bit, but this is another concept in this chapter, and that is the formation of ionic solids and the Born-Haber cycle. What I will ask is that you're able to do the steps that you see here and to calculate an overall net reaction and energy for that reaction. So I'll go through the steps here, but also note that on page 119 in your text talks through each of these steps as well. So if I go a little fast for you, they are also noted there on page 119. So we're forming an ionic solid, and there are specific steps that are always the same here that you will see. And we haven't talked much about thermodynamics or chemistry of that yet, but the energy values that you see here can all be added together to give you an overall net. And I'll explain what I mean by that. You can see the numbers 1 through 5. These are the stepwise reactions that we use to model the formation of this ionic solid. So the first is solid sodium to gaseous sodium. And this is important because we have to have gaseous molecules to react in order to form this ionic solid. And there's an energy associated with that reaction, 107.3 kilojoules per mole. These reactions that you see and the energies that you also see would be given to you. And it's just a matter of arranging them in the right order and then summing them correctly to give you the net total. And I've given you a couple examples in the pre-class and on the homework with these, and obviously there's some in your chapter as well. The second step is taking that chlorine gas. Recall chlorine is one of those that occurs as a diatomic molecule, and splitting it up into a single chlorine gaseous molecule. And energy associated with that is 122 kilojoules per mole. So the first and second steps are taking the elemental phases of these compounds, in this case solid sodium and gaseous chlorine, and converting them into single gaseous atoms, respectively. The third step there, if we look at that, so that's gaseous sodium, and it is losing an electron, and there's an energy associated with that. Recall that we talked about ionization energies, and we said that's the amount of energy needed to remove an electron. That's exactly what you're looking at here. So 495.8 kilojoules per mole is the ionization energy for sodium. So it's reflected there. That's the reaction for removing an electron, forming sodium with a +1 charge. The next thing we need to do is form chlorine with a -1 charge, because those, again, are the two things that are going to combine together. If we look at that one, we see chlorine gaining an electron to form chlorine gas. And we just talked about electron affinities being the energy that's released when we add an electron to an element, and that's exactly what's represented here. So minus 348.6 kilojoules per mole is the amount of energy that's released, or the electron affinity that chlorine has. And then lastly is the combining those two gaseous ions together to form that ionic solid. Excuse me. And this is just a measure of those the electrostatic interactions there. So those two ions coming together to form that ionic solid. And the amount of energy that's released there is 787 kilojoules per mole. I should have said before now that the signs on these numbers matter. So the 107.3, the 122, and the 495.8, these are all positive values. The 348.6 and 787 are negative values, and it's really important to keep track of these charges. What you're going to do when you come up with the net, if you see there that net reaction and an overall net energy of minus 411 kilojoules per mole, that's obtained by adding 107.3 plus 122 plus 495.8 plus a negative 348.6 plus a negative 787. So do those out on your calculator and check your math and make sure that you come up with the minus 411 kilojoules per mole, and hopefully there's no typo here. But that's how you calculate that the overall net energy of this whole reaction, of this cycle. And you need to be able to do that from these reactions. The net reaction, what you can do here is just look at, you can sort of add all the reactions up. One way to do this is to just actually write them all on top of each other, and then anything that's on the left and right hand side of an arrow will cancel each other out, and you will end up with the net reaction that you see there, a solid sodium, half chlorine gas, giving you the sodium chloride solid. Okay, the arrows, so the red is to indicate energy that's input into the system. The darker blue, this is energy that's released. These are sort of showing you the steps that are not thermodynamically favorable in red, and the ones that are thermodynamically favorable in blue. They are shown generally to scale. So you can see overall you have a net reaction that's favorable, that gives off energy. And that's what's shown in the lighter blue arrow. So the difference from where you start to where you end up. And that's just commonly a way to show this reaction. This is written out, as I said, so here's sort of in diagrammatic form. Here's taking all of those 5 reactions and steps and writing them out so that you can see them how they sum together. So on the far right are the thermodynamics, so these give you the energies, and you can see how that sums to minus 411. And then the reactions themselves, again, just written out as you saw before. And if you sort of go down through, you can see, for example, in step 1, see the sodium gas as a product would cancel with the sodium gas as a reactant from step 3. So that would remove that, one. And if you do that all the way through, you would end up with the net that you see on the bottom. Another example, if you look at the sodium ion gas in step 3 as a product, is a reactant in step 5 on the left-hand side. So that would cancel out. So that's one way to go through that. You can actually just write these out and, with a pencil kind of put a slash mark through the left, what appears on the left-hand and right-hand side, and then see what's left, and that's what you write as your net reaction. Lattice energies, so I'm not going to ask you to calculate these, but this is the amount of energy that's needed to break up an ionic solid into its gaseous ions, measured in kilojoules per mole. And as I thought, that's the end of the chapter. So again, in terms of the Born-Haber cycle, I think I gave you a few of those on the pre-class. Certainly ask questions if you have them on how to do those. There is a formula, Coulomb's law, that's written in your chapter. I will not ask that that you can do that. And again, the chemistry part, so the remaining sort of sections of the chapter, I won't ask you on the exam. In terms of the learning outcomes from this chapter, just sort of going down through these, the only one that sort of wouldn't apply is the last one, because we didn't discuss the reactivity of the groups, as I just said. But the rest of the outcomes that you see there are ones that we've talked about and you should be able to do.